Okay, these are the trig notes over sections 8.4 and 8.5, the different types of geometric series. 8.4 is about the finite case, where 8.5 is about the infinite case. Now there's a couple other different types of infinite series that are in section 8.5, but we're really not going to focus on those. We really would like to focus on the finite case for geometric and the infinite for geometric. Well, you might see something that looks like the summation notation in regards to, as n goes from 1 to 25, so we're talking about 25 different terms. Starts with 2 and it has a multiplier of 3. So we plug in a 1, we get 2. Plug in a 2, we get 6. Plug in a 3, we get 18. Plug in a 25 and you get a really large number, something close to 5.65 times 10 to the 11th. And we're going to add all those numbers up. Now, there is a quick way to do that. You're going to be using this formula. The sum of the n terms, the n finite terms, is equal to the first term times the quantity 1 minus r to the n power over 1 minus r. That's the formula we're going to be using for all the finite cases. Now the infinite cases might look like this. Still summation notation, but as n goes from 1 to infinity, sorry for the scribble, of 4 times 1/2 to the n minus 1. Well, the first term in this case would be 4. You plug in a 1, you get 4. Plug in a 2, you get 2. Plug in a 3, you get 1. And continuing on, you see the dot, dot, dot indicates that it goes on forever and ever and ever, never stops. That's called an infinite geometric series. I'm sure at this point you're probably thinking, how can an infinite group of numbers add up to be a number? Well, it's the idea of the limiting value or approaching a limit. Now, there are two cases of the infinite. There's the case where the absolute value of r is less than 1 and the absolute value of r is greater than or equal to 1. Now, keep in mind, what does this one mean? This, since the geometric sequence is a lot like the exponential model, this would be indicating that the sequence of values follows a decay pattern, whereas this one would be talking about a growth pattern. Okay? Well, let's see. Let's look at this formula that I had a few seconds ago over here. And what happens if r, the absolute value of r, is less than 1? In other words, when you raise n to a really big number, a fraction raised to a really big power, it disappears to 0. We talked about stuff like that in section 8.3. So, this pretty much is gone from the equation. And what is g sub 1 times 1? Yes, that's right, g sub 1. So my equation on this next one gets really a lot simpler. We have s sub infinity, use the infinity symbol here, equals g sub 1 over 1 minus r. And there's my equation for the infinite case, but it only occurs if that's true. If you're in the other case, where the values of the terms keep getting bigger and bigger and bigger and bigger and bigger, and you're adding them and they keep getting bigger, well, guess what? That diverges. That doesn't even have a possible chance of getting close to a particular number. So, two different cases for the infinite, and you need to know that when the absolute value of r is less than 1, you have a formula. And when the absolute value of r is greater than or equal to 1, you have no formula to use. Okay, so this is 8.4 example 1. Since I see there are 7 terms, we're looking at the sum of 7 terms. We've got the first term when we plug in a 1. Always plug in a 1. Don't ever trust that the number sitting here is the actual number of the first term, because I could mess with this exponent and you would not really like me. So make sure that you plug in the number 1 in order to check that out. But the first term in this case is 18. We have, 1 minus 1/3 to the 7th power, all over 1 minus 1/3. So we'll calculate that here. All right, we'll do this calculation together. 18. You know what I'm going to do? I'm going to do this separately. So let's see here. 1 divided by 3 in parentheses to the 7th power. Okay, figure out that value. I want 1 minus that answer. I don't know if many of you know how to use the answer feature, but it's right next to the negative sign. It says ANS. If you take a look at your calculator, you'll see the ANS feature right there on the negative. Okay, that's what I'm using. And so I want 1 minus the answer there times 18. So I've figured out the entire numerator first. Now I know that 1 minus 1/3 is 2/3, but even if you don't know that, you can still, as long as you use parentheses, type in 1 minus 1/3 and let it calculate it for you. Okay, so we're talking about 26.988 approximately. Now, example 3 in the book is probably one of my favorite examples of all time. There's a couple really good ones in the book, but this particular example, and I may get interrupted here in a second because of class coming in the room, but it says, see if I can get it on screen here for you. The maximum number of natural ancestors that you could have are 2 parents, 4 grandparents, 8 great-grandparents, and so on. Assuming that no one appears twice in your ancestral tree. Yeah, that would be gross. I can't believe that, but they had to actually say that. When the fork in the family tree comes back together, that's not really usually a good thing. So it says, in the last n generations, you have S sub n natural ancestors, where S sub n, S, capital S standing for sum, is 2 plus 4 plus 8 all the way up to 2 to the n. How many generations must you go back before you have 1 million natural ancestors? Assuming, once again, no one appears twice in the good old family tree. So, that was a pretty good one. The fork and the tree coming together, huh? Alright, so let's see here. What do we have? We've got a first term of 2, right? You've got 2 natural parents. And the multiplier between the terms is also 2. We also know, so we're using the finite geometric series formula. What we're trying to figure out is when we will have 1 million natural ancestors. So that's the sum of all the generations. First term being 2. We don't know what n is. But now we're going to go about solving for this. Okay, so we've got -1 down here in the bottom. And so 2 divided by -1 is obviously -2. So I'm going to multiply both sides by -1/2 in order to get that down to -500,000 equals 1 minus 2 to the n power. A little adding and subtracting kind of flip-flops these two things. So that says 2 to the n is 1 minus negative. Is that right? No, that'd be plus. Yeah, I was right. 500,000. So 2 to the n equals 500,001. Whoops. Yes, of course we're going to have to use logarithms. What self-respecting math person wouldn't want to use logarithms? Got to change it from its exponential form to its log form. My calculator won't handle base 2, so I take log of the argument over log of the old base. So, let's see here. Find my graphing calculator machine. Log 500,001 divided by log 2, and we're talking 18.93. So in 19 generations, which actually seems surprisingly low, but 19 generations you will have 1 million natural ancestors. Assuming that the fork in the tree doesn't come back together, you know, that kind of thing. Alright, let's look at examples in section 5. So moving on from the finite case to the infinite case. You can clearly see from this summation notation that it goes from 1 to infinity. It is geometric, right? 3 times 1/2 to the I minus 1. The big question we have, as we talked about earlier, was, is 1/2, the absolute value of 1/2 less than 1? Of course, the answer is yes. Therefore, we can go straight to the infinite formula situation, right? So, first term, plug in a 1 just to check what the first term is. What if MrJStailey got all tricky on you and changed the way the formula looked? Maybe he did this. What happens if MrJStailey gets evil and does this? So you plug in a 1, what's the first term? It's 3 over 2. That would be an evil trick because a lot of children would just pick 3. So please be careful and plug in a 1 in order to check what the first term is. So the first term is indeed 3 over 1 minus r. So we can find out that 3 divided by 1/2 is 6. So that is the sum. Yes, we're talking about adding up an infinite number of values. Yes, it's approaching 6. But that's what the formula says. Example 3. Example 2 is kind of a weird one, so I'm going to skip that one. But in example 3, it says, because of air resistance, the length of each swing of a certain pendulum is 95% of the length of the previous swing. So, back and forth, right, until you get all sleepy. Okay? So anyway, we've got the pendulum, and so we're measuring the swings. Obviously, gravity starts to slow it down, and the air resistance is also grabbing onto it. If the first swing has a length of 40 centimeters, find the total length of the pendulum, or total length the pendulum will swing before coming to a rest. In other words, each time it swings, it's going 95% of the previous swing, and so they're slowing down, but you're adding all of them up. Is the absolute value 0.95 less than 1? The answer is yes. Therefore, we can go immediately to the formula. First term. Well, the first term, the first swing was that 1 minus 0.95. So, we get 800. Please keep in mind, if the absolute value of r is greater than or equal to 1, what happens? Then S sub infinity diverges. You will not be finding anything with the formula. Trust me, I've got kids that don't follow my directions. They get to the test. They think they're supposed to throw things into the formula. The question ends up being a whole bunch of positive numbers that add up to a negative number. And they don't even think about that. And so I'm sitting there looking at him going, why didn't you just realize this and write down it diverges? So I don't want you to lose the credit like they have in the past. So please be careful. Look for the absolute value of r. Test before you use the formula. And thank you very much.